today's discussion we will continue where we stopped yesterday, and this is about evaluating stacking fault energies. So, the way I have set this session is that we will just talk about stacking fault first, and then we will talk about what is known as generalized stacking fault energies, which are stacking fault energies at 0 Kelvin. And because it is at 0 Kelvin and we are looking at classical particles, the stacking fault energy is nothing but the bond energy or potential energy difference. You have a perfect crystal, you have a crystal with stacking fault, you calculate the potential energies, you take their difference, you will get the stacking fault energy. And because it is static and you do not have to worry about vibrations, you can do a little bit better than just getting the stacking fault energy. You can follow the path that you need to take to create a stacking fault energy, which means in addition to stacking fault energy, you also get the barrier energy. That is very, very important in some cases. I will also show an example this afternoon how important it is to know what this barrier is. But because like we have been telling, MD, MC, energy is already part of the calculation. So, you can always get, you can get more involved calculations you can do and get the energies. The problem is when it comes to evaluating entropies and hence free energies, which is important at any finite temperature. So, that is the next part, which is the stacking fault energy evaluation, for which we need the free energy evaluation. And yesterday we saw that there is reverse scaling which can be used to get free energy as a function of temperature fairly easily, and Frankel-Lott path will get you the free energy at any given temperature which is non-zero. Okay. By starting from Einstein crystal we will reach. So, these two methods will then help us evaluate free energies as a function of, as I will show you a case, composition and temperature. Okay. So, why is it important in this system, etc., is also part of this discussion, because we have been spending some time. So, there are many different aspects. There is a statmic basis from which these methods are coming. There are numerical techniques like how we integrate these equations. There are computational issues as to how we deal with some specific, like for example, maintaining temperature or something like that. And then there is the material science aspects, which also we need to understand to do proper simulations or be convinced that we are doing sensible things. So, let us start with stacking fault. How many of you have heard of stacking fault? Okay, very good. Okay, some 4, 5. So, for the rest, the idea of stacking fault comes from visualizing the crystals in a slightly different fashion, right. If I ask you what is a cubic crystal, for example, you will say that take a cubic lattice and put atoms at the corners or at the lattice points, right, of a cube, and if you stack, then you will get this cubic lattice where every lattice point is containing one atom or one motif. I mean NaCl, for example, can be Na and Cl, the molecule you put, and you will get the lattice. But there is another way to think about the crystal structure, that is to think of stacking. Let us say that I take 4 atoms like this, and then I keep stacking one on top of another. You will also get a cubic crystal, right. So, you can imagine the cubic crystal structure as a simple cubic crystal structure as a stacking of these atoms in the 100 direction or 001 direction, whichever way you want to think about. Okay. So, you can take this in 2D, right, this is repeating, and then I keep stacking them. Okay. That is how to understand simple cubic structure using stacking sequence. You can also think of stacking sequences in other directions, which is what is of interest to us. So, the way we want to imagine this is that I want to consider an FCC crystal right, and then there is these space centers. Right. You can imagine stacking along the 1, 1, 1 planes. How does the 111 plane in FCC look like? Right. It has this kind of structure, that is what you will see if you make this 111 plane. Okay. I mean, this is, for example, is this. Okay. Now you can see that there are triangles which are like this, there are triangles which are like this. Arbitrarily, we say that this plane is an A plane, and then you can put all these triangles which are pointing downward and make another this kind of hexagonal structure, and this will be called as B, and you can imagine the stacking of FCC by putting another one, the third layer, which is here, the upper facing triangles, that is known as C. This is very intuitive. You can go to our vegetable shop. Our Tiwariji is arranging the oranges like this. Okay. He puts one layer and then he finds the places where he can put, and if he picks one sequence, and after B he might decide to go back to the A position again and stack. If it is stacked like that, if you look at the HCP crystal structure and look at how the basal planes are stacked, they are stacked like this. If you look at FCC crystal structure, if you look at how it is stacked along the 111 direction, it is stacked like this. This is very important to remember. Stacking sequences are not always 111, FCC is 111. Okay. If you are looking at stacking sequence in BCC, probably you are looking at some 110 direction stacking is probably easier to think of, and similarly simple cubic 001 is easier to think of. So, you just think of the crystal structure as a stack of atomic planes. Now, because this and this, the only difference is after I put the A, whether I use only one of the triangles and then go back to A, that will be HCP, and if I use both the triangles ABC, then I will get FCC. Sometimes there is a fault in this sequence, that is called a stacking fault. That is because suppose the C is left out and then you start again, that region locally looks like a HCP region, that is a stacking fault. So, the stacking fault in FCC locally looks like an HCP region. Okay. So, for our purposes, this is what we mean by stacking fault. Okay. Now, why is it important? It is important because in FCC, if you are looking at deformation, then what is the Burgers vector? Let us assume that the deformation is by dislocation. So, dislocations have to move. What is the Burgers vector in FCC? Half 110, right. So, half 110 is the Burgers vector. I should not use the plane. Okay. Now, this half 110 splits into partials. Why does it split into partials? Minimize the elastic energy. So, you can see that elastic energy which goes as mu b squared. Suppose if you can write this b into suppose you have two meaningful vectors, I mean these should be legitimate vectors of lattice positions in the FCC lattice, which you can see here. From here you can go here and you can come here. Okay. This is the full vector, this is the two half vectors, they happen to be 1 1 bar 2. So, you can put 1 1 bar 2 here and calculate the elastic energy, you will find that it always is smaller. So, a full dislocation splits into partials, and these are known as what partials? Shockley partials, right. So, these are known as Shockley partials, and because these Shockley partials form and they are of the same type, right, they will generally tend to repel each other. Once the partial forms, they have to repel each other, so they will go apart. But as you can see, because this is also is the sequence related, if you move a dislocation here or bring in an extra plane there, then you get a stacking fault in between these two Shockley partials. So, in systems like this FCC, dislocation splits, that is because energy is always minimized. Then these two dislocations partials are of the same type, so they repel each other. So, they try to move apart, and dislocation interactions are infinite. So, they can keep on moving to infinity. That does not happen because when these partials move, the partial movement basically takes atoms which are on a B plane and moves them to C positions, which means it creates a stacking fault, and so the partials move and you have a stacking fault in between. The stacking fault is a surface, so it has its own energy. You can think of it something like a surface tension. So, it does not want to move, so it pulls these partials. So, there is an equilibrium that is achieved, and that is how experimentally sometimes people determine stacking fault energies. You go look at the stacking fault, the partials and how far apart they are, in between there is a stacking fault, then you do a force balance. Okay, this is the force that is acting, pulling these two dislocations apart, this is the stacking fault region. So, this must be the energy, that is how we evaluate. It is a bit tricky, I will show you some experimental data which can be conflicting. In earlier days when people could not measure very accurately, there have been wrong, I think wrong measurements, more recent measurements give different values. Any case, now how far these partials separate also then becomes important in the deformation behavior of the material, because if sometimes the dislocation has to cross slip. What is cross slip? Instead of moving in one plane, it has to move to the next plane above or below. If it has to move, then if these partials are separate, then they have to come together, form a full dislocation and move. And now if the stacking fault energy is low, these two are very far apart, so they cannot cross slip that easily. Whether the dislocations cross slip or do not cross slip will have a say on how the deformation behavior of the material is. So, because of which it becomes very important to know what is the stacking fault energy, how much is the stacking fault energy. Okay. So, that is why it has been measured experimentally very carefully, and now this also takes us to another mode of deformation which is known as twinning. You can think of a twinned region. So, twin boundary is basically a special kind of grain boundary. Across the boundary, the orientation of the unit cells are different, but it is special in the sense that it is a coherent boundary, which means there is continuity of atomic planes, just their orientation changes across the twin boundary. You can think of a twin boundary as the two parts, the two boundaries that enclose the twin can be thought of as very close to stacking faults. I mean, they are not strictly stacking faults as you would see, but they are very close to stacking faults. So, in systems where stacking fault energy is low and the partials are far apart, you also have a tendency that they will form twins, which means when you deform, they will also have a tendency to deform by producing twins. The plastic deformation will be accommodated by twinning instead of moving dislocations. Okay. There is one more mechanism which is the transformation, which is a phase transformation can happen, which is common in some steels. For example, you try to deform, the material will undergo martensitic transformation. It so happens that some of those martensites also, epsilon martensites, which are HCP structures which show up in a cubic system. So, austenite to martensite also has the same FCC to HCP relationship in this system. So, because of all of which it becomes very important to have a much clearer idea about stacking faults when we are dealing with deformation behavior studies. Okay, so that is why we are interested in stacking faults. Here is an example of copper and copper aluminum, where the twinning is happening because of deformation, and these are very high strain rate deformations. You basically explode something or impact something, and then look at what happens to the deformed microstructures. You can see that in copper you do not see so many twins, but in copper aluminum these are the twins. Okay. So, you see lots of twinning that is happening, and that is what is shown. So, pure copper and up to some 2% atomic percent aluminum, you do not see twinning for this strain rate. Okay. Why are we doing explosion or impact loading? Because that is very high strain rate deformation, and typically there is high strain rate and low temperatures is where you will see predominantly twinning in this kind of FCC materials. This is copper. Silver is a system which is considered as a low stacking fault material. So, but it is the stacking fault energy is so low that the rate at which you form the twins are also the rate at which you can destroy them or something close enough. Okay. So, sometimes even though it has very low stacking fault energy, you do not see so much of twinning, because twinning and detwinning happens. This is just partials moving this way and that way. Okay. B goes to C and then it goes back to B again. So, that can also happen. And very high stacking fault energy materials obviously do not twin, because the stacking fault is costly and twin boundary is almost, I mean, you can think of one twin boundary energy as 2 stacking fault energy or something like that. Okay. So it is costly and it does not happen. So, there is an intermediate regime where you see predominantly twinning, and especially in this intermediate stacking fault energy materials, experimentally you will see twinning at low temperatures and high strain rates. That is a combination which will lead to twinning. Okay. Remember this, because this is important for us later. But 4 and 6 atomic percent aluminum, you strain to different percentages and you see that lots of twinning is happening. So deformation behavior is changing with aluminum addition, and the argument here is that aluminum is changing the stacking fault energy. That is why the deformation behavior is changing. It is shifting from dislocation mediated plasticity to twinning mediated plasticity, right. And in this, I mean, this system is very nice for us, because we are in a regime, this is a copper rich end of the phase diagram. Aluminum rich end is also very important. These are the duralumin kind of aluminum copper alloys which are used in the aerospace industry, and it's a long story by itself, how these precipitation hardenable alloys were discovered and how they change the physical metallurgy and alloy design and so on. Probably Ferdi will talk about it sometime. Merca and this thing, and accidental discovery of this edge hardening at room temperature and so on. So, this is a very fascinating part of the phase diagram to the left end, but that is not what we are paying attention to this time. We are looking at this end, which is a copper rich end. These are called copper aluminum bronzes, okay, aluminum bronzes. So, we add aluminum, and you can see up to some 82% or some 16 to 18 atomic percent of aluminum, the material still remains in FCC crystal structure, single phase. So, that is why we prefer. After that, the stacking fault energy becomes negative, which means it can spontaneously form lots of stacking fault energies, which is equivalent to saying that it is going from FCC to HCP. That is why there is an alpha at low temperature, you can see. At high temperature there are some other phases, I think beta is BCC or something, Sushil? In the high temperature, what is that phase? BCC, is it? That beta, what they call? Or some ordered intermetallic, yeah. So, at low temperatures it does go into this HCP phase, which is an indication that the stacking fault energy has become negative. It goes down and then it becomes negative, then the system will spontaneously undergo a phase transformation. Okay, that is what is happening. So, that is why this is a model system. Cu3Al9, yeah, some ordered structure. So, which is also of interest. Okay. But we will not talk about it. We will only talk about the low temperature. 300 Kelvin is where we are interested in, and we are looking at, and because it is a single phase in which you can methodically change the stacking fault energy with alloying, it becomes a nice system to study. Everything else more or less remains the same, only the lattice parameter, Burgers vector, and the stacking fault changes predominantly, and then you can study the system. So, that is why this is of interest. And of course, people have measured stacking fault energies, and this is what I said with aluminum percent. For example, people have reported stacking fault energies as high as 78 millijoules per meter squared in copper, but I think I would believe the other studies which show that this is somewhere around 40 millijoules per meter squared. There are lots of technical difficulties in finding the distance between the partials, because that has to be done using transmission electron microscopy, and so if you are not careful or if you do not account for all sorts of experimental artifacts, then you can get numbers to be really bad, and they are twice the amount. So, Rohatgi et al. Report something like 78, and I think that is not quite right, but probably in copper aluminum the stacking fault energy, and this is also corroborated by first principle calculations, for example. So, it goes somewhere from 40 millijoules per meter squared to 0 over a composition range of 0 to 12-13 atomic percent. Okay, even though phase diagram shows that it is about 16 to 18 atomic percent, we also found that for the EAM potentials we use, for example, beyond 10%, 12%, etc., if you put, then we do see that the stacking fault energy becomes negative, and system, you do not have to do anything, it will all some jostling and it will become all HCP and so on, or lots of stacking faults, twins and so on. Okay. So, from atomistic simulation, then our aim in this problem, for example, is to get the stacking fault energy. And like I said, at 0 Kelvin, the stacking fault energy is nothing but the difference in the potential energy. If that is so, stacking fault energy is when I have moved all the B plane atoms to C positions and then I created a stacking fault, I can measure, but at 0 Kelvin I can do one better. I can start from this point, I end up at this point, at every point in between I can measure the stacking fault energy. This is known as generalized stacking fault energy, and this is important because sometimes or most of the times it is also important as to what is the barrier that the system has to overcome. Okay, you have some reduction in energy if you go from this state to that state, but how much is the barrier you have to overcome. So, in the initial stages when MD simulations were done and the results were not consistent with what you would expect, the stacking fault energy is lower in one system, but you do not see so many partials forming and so on, or so many stacking faults forming and so on. Then people realized that it does not depend only on this, but also depends on the barrier. So, barrier has to be calculated, and because at 0 Kelvin you can do a molecular static calculation. I start ABC, then I pick one of the B atoms and start moving slowly towards the C atom in steps. At every stage I calculate the potential energy, and then when it hits the bottom I would have reached another minima, and from there you can go one more or you can come back to the position, and that will tell you, if you come back then you will get the periodic potential. So, you will have one between and then you will come back, and if you keep the fault, that is sometimes it is called the leading partial and trailing partial, and there is a reason why one of them is the leading partial and one of them is the trailing partial. So, do any of you know why is there a leading partial and trailing partial? It is related to the structure. You have heard leading partial and trailing partial? Most of you who have heard about stacking faults and partials. So, which one is the leading partial, how do I decide, or which one system chooses and why? Right. I said that this is the partials, right? Why is it going from lower to higher? They are all going to stable position. This is a stable position, this is a stable position, this is a stable position. That's not the case.
Think of interchanging these two vectors as translation vectors.
Think about it. If I remember correct, if you move the trailing partial, one atom comes on top of another or something, right?
You see it here. I mean, if you do the, you have this vector starting from upwards and then downwards.
Yeah.
If you do instead first go downwards,
This one,
you end on the big.
Here, right? This way.
So you have two atoms on top of each other, which is quite unfavorable.
So, given two vectors, you will know which one is the leading, which one is the trailing. After that leading moves, the other one can move here because it gets a minimum energy position. Before that, if you try to move, I think it comes one on top of another, so that is not possible or favorable. That is a trailing. If you try to, instead of taking this, if you take this vector and try to move this, that comes on top of this atom, right. So, that is the trailing partial. So, it cannot do that because it is going to a much higher, right. You have seen those GSFE surfaces, right. There is a barrier which is higher, that is the hill. These are the valleys through which you travel, so that you can avoid that. So, it will not go through this. Okay. So, GSFE is important in trying to make sense out of some of the behavior of materials, and as you can see, because it is a molecular static calculation, you can do it very nicely and get. I will also show you a model script that I found online. I will also share the script that Kamalakshi has developed. There are small differences between what is there online and what we have done. Sometimes it might be important for you. And at finite temperatures, of course, free energy evaluation is important because that is how you will get the Stackingfault energy. Okay. So, at 0 Kelvin, how do we get the GSFE curve? Like I described, the process is simple, and this is what I said. General script that I am going to show you calculate Stackingfault energy using boundary conditions P, S. So, it is periodic in the x, y, and in the z direction it is not periodic. It is a shrink wrap. Okay, no atom can escape, but it is a free surface. But because we also wanted to use this system and calculate, do the thermodynamic integration and calculate the Stackingfault energy and so on, we did not want this free surface on top. But if you use periodic boundary conditions, sometimes it is very difficult to avoid at the periodic boundary the atoms forming another Stackingfault, or sometimes in some unfavorable positions and so on. So, in the GSFE you can simply ignore some number of atoms far away from the Stackingfault, and that is what is shown in this box. You leave out these atoms and you calculate the potential energy for the remaining atoms before the creation of Stackingfault, and at every step take the potential energy and plot, and you can get the GSFE curve, which also agrees with this PPS. I mean, in the S case also, if you put the surface quite close to the Stackingfault, you will get wrong answers there also, because I mean surface will relax. It has to be far off, because of which what happens at the boundary is not important. So, you can put shrink wrap, you can put periodic boundary condition, you can get the same results, which is what is shown in the next figure. There is one evaluation we have done using the PPS boundary condition, another evaluation we did with PPP, but leaving out this box. If you do not leave out, you do not get the same curve. okay, because those atoms which are sitting at some really unfavorable positions raise the difference in energy to a large extent, and the red curve is just the polynomial fit to show you. Now, you can see that the bottom, this point is one of the B positions, and from there it has gone to C position, that is the minimum. So, difference between them is basically the stacking fault energy at 0 Kelvin. But what it also gives is what is the barrier it has to overcome. If it is the set of atoms slide, how much is the barrier it has to overcome to go fall at that point. Okay. You can have this difference to be the same, but if the barrier is different, the one with lower barrier will tend to have more of the, which is obvious now, but I think it took some time for people who are doing molecular simulations to realize, and Strikingfault is one of the names I remember. I do not know if she is the only one who did, but there were about 20-25 years ago lots of papers which explained the importance of getting these curves. Nowadays GSFE curves, but I think GSFE idea itself goes back to Schoak. So, I have seen some papers from Schoak in 60s, 70s I think. So, the idea itself is old, but it became important, people realized that this becomes important. So, you will see online lots of WASP codes, the first principle codes to calculate this, and we also use some of it for our phase field dislocation dynamics studies, where this surface over which the dislocation is moving is important. So, we get them the generalized stacking fault energy curves from the first principles calculations. Of course, you can also get it from the molecular dynamics calculations. Only thing you have to remember is that unlike the first principle calculations, MD calculations are dependent on the potential you use. Okay. And like Ferdy mentioned, if your potential is not good for capturing stacking fault energies, you can get all sorts of strange results. This is something again in the literature is not there, or we notice that sometimes people are not careful, but because you are learning and you will be doing, it is better for you to learn at this point. One of the main claims in Kamlakshi's paper that we made is that people do deformation experiment, simulations in MD, and then they take experimental values for quantities such as stacking fault and then start interpreting. Now, if you used a EAM potential and if you did your simulation using that EAM potential, to be consistent, you should use all quantities derived from the same potential for interpretation. You can't use some from first principles, some from experiments and some from 0 Kelvin and start interpreting, okay, which is done in the literature. So, to be consistent you have to do, that is why the free energy evaluation and stacking fault energy for this potential at that temperature, that is what the actual system is experiencing, and that is how it is giving some deformation behavior. So, to make the correct connection between what is happening and what the energetics is, it is very, very important to evaluate all the quantities using the same potential, which is not the standard practice in the literature. Sometimes people take values from experiments from first principles and start interpreting. That can lead to problems, especially because you do not know what your EAM potential actually is like for this particular quantity. So, it is better to evaluate. Okay, once you know this, you can evaluate for different systems. It is not very clear here, but there is a technical issue with anything other than pure copper. Can you think of, if any of you do first principles also, you will know. So, the process is very simple. I generate a structure like this, which did not have a stacking fault, then I choose one particular plane and slide B atoms to C positions 1, 1 bar 2 or some such vector I take, and I start moving it in that direction till it completes that vector, and then calculate potential energy at every point and then draw the curve. That is all I am doing. For pure copper, no issues, but the moment you go to some amount of aluminum, there is an issue. Can you think of what the issue is? Right. So, what is the problem with that?
The
related to statistics. How will you set up the simulation? Let us say I want 2% aluminum. How do I set up the simulation? We randomly distribute 2%. Now you choose a plane. Will that plane have 2%? Will you have 100 atoms in the plane in the first place? Okay. Right. So you have to do statistics because you randomly distribute and you choose the same plane. In the plane and in the vicinity of the plane, the number of aluminum atoms could be different in different realizations. Right. This goes back to the ensemble and time average. You can take this and then do lot, its equilibrium done. I calculate, I will get some number. You do another random seed, you will get a number which is slightly different. This is not the case with experiments, or at least we assume that in experiments all possible realizations have happened, and I do not know if you do for with some aluminum these spacing of partials also, whether you will see differences depending on how many aluminums are there. And in this case it is worse because aluminum prefers to go sit in Stackingfault, which is known as a Suzuki effect, which is something we will learn next week. I will also show you scripts, and that is from Sushi's thesis work. So there is a error bar that comes in, and that error bar is simply because of statistics. You say 2%, there are so many different ways of putting 2% of aluminum atoms, and there are so many configurations that you will have near about the stacking fault in terms of number of aluminum atoms in the stacking fault itself and number of aluminum atoms and how they are distributed around the stacking fault. So each of those points are to be done with large number of simulations, average out and plot with error bar. Okay. Pure copper, there is no problem. I mean, there is only one way of putting aluminum copper atoms, and so it does not matter. Okay. So you should remember statistics becomes key, and you should always think, okay, I am doing this, is this sufficient? I said 3 simulations, maybe in this case even 3 is not sufficient. Okay. And we have also seen methodical increase in error bars with increasing aluminum concentration, which basically tells you that your system size is small, and these local configurations can sometimes skew your results. So you need to do many more simulations to keep the error bar under control. Okay.
What was your simulation box size?
Simulation box, I think she used 30 by 30 by 60 unit cells.
So the Stackingfault itself has 900 atoms.
Yeah. Yeah.
Why it's not following a single curve with a larger error bar? Why the activation energy itself is if I consider that it is because of all the statistics, then it should lie on 0% copper and the error bar should have up and down.
No, okay, I didn't get your question. The error bar is, I am drawing one line, I am saying that that line has a thickness, right? Okay, that is the error bar. Why is it related to the barrier? It need not be, right?
Barrier itself is in relation with
Yeah, I mean that is what we see. For these potentials, it shows that the barrier height also increases, okay, and the barrier height decreases, okay. So and the stacking fault decreases because copper has the highest stacking fault energy, so it also has the higher barrier, okay. So which means that not only the stacking fault energy decreases, which means the partials will get separated farther apart, so you will have larger stacking fault region. It is easier to create these stacking faults because the barrier is also lower, and I will show you that this is the case, and to explain the deformation behavior correctly we need to take into account this barrier height also. Afternoon I will show you that. Okay.
Drastically change
Change it.
Stackingfault
Yeah, and we have when we do the Suzuki effect, the binding energies, etc., it does have a large effect on, yeah. So, okay. So these are things that you have to keep in mind. I mean, like I said, you will see the generalized stacking fault energy script online. It took me 5 minutes to find one, okay, and it took 2 minutes for me to download that potential for aluminum. In one afternoon, you now can go set up a generalized stacking fault energy curve. That is not the key. At some point, it is the materials knowledge that you have, and you have to think. Like I said, every MD simulation is like an experiment. What is it that I am setting up? What is it that I am calculating? What is it that I am measuring, and how am I doing it? And does that make sense? Okay. So, this you have to keep, and statistics, of course, always is at the back of this, because this is all based on StatMech anyway. Okay, so that is as far as generalized stacking fault energy is concerned, and maybe at this time I can also show you the script that I downloaded from online. I haven't tried running it. I will try to run it in the afternoon. I will probably show you. So, this is available online. Okay. So, this is the stacking fault energy for aluminum, and now you know, like I said, this is the boundary PPS, and the atom definition and the force field is aluminum, and then you make two regions, top and bottom, and you start moving. I think he moves the top and calculates energy by doing the minimization. Okay. That is all there is to it. I mean, like I said, it is a very simple calculation. It is a static calculation like our lattice parameter calculation. There is nothing, no molecular dynamics loop at all. You just move, calculate energy, print it out, and you need the potential, and the potential is there. So, let us go back to stacking fault energy calculation at non-zero temperatures. At finite temperatures, that requires either thermodynamic integration or one of the non-equilibrium evaluations. And here, this is a question I left you with yesterday. So, you saw that typical stacking fault energy for copper is 40 millijoules per meter squared, and if you take a stacking fault area of 80 nanometer squared, the free energy difference that you have to evaluate is of the order of 20 electron volts. Okay. But on the other hand, in the copper aluminum alloy, when you go to higher amounts of aluminum, the energy, the stacking fault energy can become 6 millijoules per meter squared. So, it will come down to few electron volts. So, that much difference you have to be able to accurately calculate. What makes it worse is that in the copper aluminum alloys, when you have some composition of aluminum, because of this distribution, to get to that accuracy, to reduce the error bar, you need much more of simulation. Either first place the difference is very small, second place your error bar is large, because you know you have a finite system and you are distributing these atoms. So, it has to be done very carefully, otherwise you will get all sorts of numbers. Yep. Of the order of, yeah. No, 40 millijoules per meter squared is at room temperature. As the temperature goes, they also tend to, I think, increase or some such strange thing. Because these are free energies, I always thought that they will decrease, but experimentally as well as in several simulations, it is reported that with increasing temperature, these stacking faults increase, energies increase, which is another strange thing. But yeah, it is at room temperature, and these simulations are also at room temperature, at 300 Kelvin we evaluate. Okay, so this is just reminder, you can take thermodynamic relationship and you can integrate. The integration requires two endpoints. One of them is of your interest, that is what you want to calculate. So, which means you need the reference point, and there are analytical solutions for typical reference points, and simulation allows you to take the system from that reference point to your point of interest, which is what we discussed. So, I just want to point out a few more technical details. Again, this is from Frankel and Schmidt, but what I want to show, all this is from the Freitas paper that we discussed yesterday. Okay. So, first thing they show, and this is a very nicely written paper, yesterday I only discussed the formulation aspect, today I am pointing out some of the things, not all the things, with respect to the numerical implementation. You have to use delta T which conserves energy to this accuracy. Okay, if you are just looking at some microstructure or something, maybe you do not even pay attention and you will broadly get MC also I have seen. The code could be completely wrong and from the microstructure you will not be able to make out. Or like what Ferdy was showing yesterday, you look at the fluctuations, they look okay, but you do careful analysis, you see that this thermostat or barostat is not doing a good job at all. Okay, so that can happen. So you have to choose appropriate delta T. First exercise is to make sure that you have chosen the right one, your energy is conserved, your integrator is not giving too much of error. Then they suggest that you use a Langevin thermostat, and also even though the ensemble is NPT, you cannot use NPT ensemble. That is because the Einstein crystal, which is a reference, does not allow you to barostat by calculating pressure using virial. Okay. Now, virial was derived for you, and yesterday Freddy also told what the Einstein crystal is. You can go back and look at why you can't use virial to calculate the pressure in the case of an Einstein crystal. Okay. I think his derivation had the answer. So you think about it. Yeah, I mean, his derivation had the answer. I mean, if you have the notes.
I think the answer is very simple.
Yeah.
Just think what was this symmetrical area?
What is virial? I mean, what is the expression you are finally getting? The derivation had force split into two parts, right? External and internal. And virial is coming from where? External is 0, it is coming from internal. So, what is the, why can't we calculate pressure using virial? No?
I mean, just think of the definition of this area. What is it?
I think he called it W or something. How was it defined? How is it defined?
Multiply two quantities and then force. And what do you know? What's the force? Einstein crystal. Are there forces?
Einstein crystal assumed
I think gas,
like ideal gas, right? I mean, the atoms were vibrating, but they were not feeling any force. And that answers Sushil's question. What is Debye crystal now? You will now add a spring connecting them, so they will feel a force. So that is Debye. Einstein doesn't have, which means you can't use virial to calculate the pressure. Which means even though this ensemble is NPT, you cannot do the calculation in NPT. This also, I think I am noticing a problem with the understanding of some of the ensembles. This also shows you that ensembles are like, in thermodynamics you can use entropy, you can use Gibbs free energy, you can use Helmholtz free energy, and people are taught that okay, Tp constant, use Gibbs free energy. This seems to give people the impression that you can't minimize energy or maximize entropy for these systems. That is not true. It is easier to do some things in this, so we do. It does not mean that we cannot use the other one and calculate. It's the same with these simulations also. I mean, it is natural to take NPT, so you will do NPT ensemble and do simulations. For some reason, if you are not able to do NPT, in this calculation what is done is that at that pressure, at that temperature, we first calculate what is the equilibrium volume. Then we do an NVT ensemble with that volume and that is equivalent. So, the ensembles are there only for us to do the calculation in a convenient fashion. It does not mean that okay, in this ensemble this will happen, in that ensemble that will happen. No, it is all thermodynamics, everything happens the same way. Your descriptions can become more complicated or less complicated depending on how clever you are in choosing the formulation or the basic free energy or whatever. Okay. So, you should not think that this is the ensemble and this is what will happen. No, whatever will happen will happen. We try to describe, then we find which is the easier way to describe, right. So that is clear here. It has to be NPT, but the simulations are done on NVT. How do we know it is correct? Because we already calculate very carefully the lattice parameter at the required temperature pressure, we use that. So, it has the right volume. So, now I can use NVT, I will get the same results. The problem if you use NVT without being careful about the size, then there will be some pressure which will affect your answers. But if you calculate the right pressure, the right volume for that pressure, you can use NVT also instead of NPT and you will not get wrong results. Okay. So, this is important to remember. These things are there in the paper, I mean they have explained that they use NVT in spite of it being NPT and so on. Many papers do not do, and even after that explanation whether it is clear to you, it is NPT, NVT are all just our convenience, we can do whichever as long as I am carefully doing it. Okay. So, I am making it explicit here. Now, the second thing somebody was asked, right, the Einstein crystal, the omega that I choose, right, how do I choose omega which is for this system or for all systems, because it is an Einstein crystal anyway I can start with whatever omega. In principle yes, there is no problem, you can choose some random omega and start or arbitrary omega and start, but the simulation, the convergence, the accuracy etc. get affected. So, you want to be as close to the real crystal as possible when you choose the reference Einstein crystal, and for doing that you need to evaluate the spring constant. And that spring constant is calculated using mean square displacement and equipartition. Next slide I have the expression I will show you, and you also have to avoid the flying ice cube problem, which is the because you are using Langevin thermostat and you were told that Langevin adds random forces or something. Yeah. So, you have to make sure that and it is supposed to do it in such a way that there is no net force, but that might not be the case. So, you have to force lamps that there should be no drift in this Langevin thermostat, okay, unless you say that, I do not think they do it very carefully. So, this paper also tells that force S or some such key you have to use to avoid the flying ice cube problem, and if you do not, you think oh Langevin thermostat, so it should be okay, there will be no net drift and so on, it is not true. So, you will get wrong results.
So fixed center of mass, something like
fixed center of mass, yeah, and you have to say yes to that. Yeah. Okay, so how is the spring constant calculated, and that is something yesterday also told me, right, F equal to kx or something. So, Einstein crystal is harmonic, so half k del r squared is equal to 3 by 2 kBt, that is the equipartition. So, you know the k. So, you take your system and you do the mean square displacements by running some equilibration simulations, using that to calculate this and use that for the Einstein crystal to begin with, so that the spring constant is quite close to the real spring constant of the system when you do this. And I think this also is one of the key parameters that we manipulate and do trial and error to make sure that we get the right results. And then the steps are very simple, and this code I have already shared. I am putting it here in the slide so that when you look at the code, if you have some question what are the steps and so on, you can come back and check. But otherwise we had long discussion yesterday about switching parameters, switching times, and how we calculate using Frankel-Lard path and so on. That is a Frankel-Lard expression, and you can see the F Einstein is 3n kBt ln h bar omega by kBt, which Ferdi derived, and there is a MATLAB code which takes these simulation numbers and does the integration finally, because you remember I also showed the integration finally is done using some kind of trapezoidal rule, sum of these. So, there is a code, and in that code all these parameters are given and we calculate this for the given system. Okay. So, it is there. Okay, I think that brings me to the end. I do not know if I took longer. No, I finished exactly in 1 hour. Rarely happens with me. So, okay, very good. Any questions? Okay, super. So, then Ferdi will take over. Some more things about thermodynamic integration and others. And afternoon we will come back, and today we are supposed to do deformation behavior simulations. Afternoon I will show you some deformation behavior simulations.
Here we see the stacking of the 1-1-1 planes. It's in German, so but I think it's easy to understand. That's what Guru showed here, and then we can look what happens if I displace the lattice along a complete Burgers vector. This would be the green one here, and you already see if you displace the red plane on top of the blue one, there's an easier way. Yeah? So this is a normal, the complete Burgers vector in this unit cell, like this. And you would take another path. This you see here. It's much easier to go first here and then go here. And these are these two partial dislocations. Yeah? So instead of doing the complete displacement in one step, you do it in 2 steps. And then if you do this first displacement, you create a mistake in the stacking sequence. This is a stacking fault. That's why I colored this plane in green. It's this initial graph, it's this green plane. So this is maybe for those who did not understand these details. Okay. It's unusual for me to sit during the lecture. Should I record it or not?
No, this they are recording. We don't use that.
Okay, because I thought you started this OBS.
No, I mean by mistake it came up, but I didn't.
Okay. So shall I start? Okay. So today I want to give 2 presentations, and I was a bit unsafe which one to show first. I have one on phonons, lattice vibrations, and free energy, which is a bit a continuation of yesterday what Guru told and also what he told right now. And then another one on diffusion. And for diffusion, you do pretty much the same things. You displace atoms from one position to the other. In diffusion, you just do it for one atom. Here for the Stackingfault, you displace whole part of the crystal against the other half or so. But the approach is pretty much the same. And I want to show this, I will do this afternoon. I want to show an interesting method besides this static displacements, step by step, how to do it perhaps a bit more elegant. And I think one could also apply it to these stacking faults. We should try, yeah? Yeah.
We should try, but except that it is a much larger region.
Yeah.
I don't know how costly the computation is.
Yeah, I was amazed how.
I think we have some 240 nodes or something available to us now, so we can do it.
I think it's even not. We can give it a try. I don't know. Okay, but now first about lattice vibrations. Yeah. I mean, we mentioned it already a couple of times. In a crystal which is not at 0 Kelvin, atoms vibrate, and I did it here for 200 Kelvin and 400 Kelvin, just a molecular dynamic simulation, recorded the positions and created this little movie here. So you see the vibrations get stronger at elevated temperature. You can even slowly raise the temperature from 200 to 600. In this MD simulations, this is done here. You see that the vibrations get stronger and stronger. So this is not very new to you, I guess. But we will try I want to try to explain how we can characterize these lattice vibrations. They are not arbitrary. Yeah? And the first approach is, I think we also mentioned this term already yesterday or so, we can approach our interaction potential by a much simpler shape, which is shown here. That's the Lennard-Jones potential, just to give an example here, which is, which can be approached by this green function here, which is not a Green's function, but a green function, green graph here, which is just a parabola. And here you see it just a close-up. If the deviation from the equilibrium position is not very big, here you see it strongly deviates here if you go by, I don't know, 10% or so. But if you go only by 1% or even less, then this approximation is not too bad. No? And this is what we call a harmonic approximation. I will explain it a bit more on my notes here. So this lecture will be on lattice vibrations. Yeah, and phonons, this term phonon, I don't know whether it's familiar to you, is just a more fancy word for lattice vibrations. Not only, it's a bit more. As we discussed yesterday, quantum mechanics also describes all these phenomena, all excitations in a solid or wherever. Yeah? And there are certain deviations from a classical system. If you go to a quantum mechanical system, one deviation was that we have these 0-point fluctuations or 0-point vibrations. Another difference is that in quantum mechanics, nearly everything is quantized, so it's occurring only in steps. For example, this Einstein crystal, the amplitude of the energy of the vibrations goes in these discrete steps. This was this I plus 1/2 multiples of the Einstein frequency times h bar, so that's the energy. But here I think more or less I use these terms lattice vibrations and phonons equivalently. So through thermal excitation, or in quantum mechanics, even at so that's the first statement. And the simplest case we discussed yesterday is that this Einstein crystal. Which is pretty artificial because it neglects all the interactions, but on the other side there is a restoring force. So this is not very clear how this should work anyhow. And of course, the reason why these atoms vibrate is given by this potential energy. So if you have our potential, like the Lennard-Jones potential or some other, if you have your distance x and the energy here, if you have an atom sitting in this potential minimum and you shift it to this side, you see it increases the energy, so Same if you displace it to the other side, there's a restoring force going into this direction, so it will always get back to its initial position. I think I even made a little animation for this. Yeah, forgot to start it here, so you see how it vibrates. This takes always a lot of time to create these stupid animations. Then I forget to show them. Okay, so, and as I already said, if you have small deviations from the initial position, from the equilibrium position, then we can approximate. Oh, maybe I should use another color here. You can approximate this potential curve by a parabola. So if you have any interaction energy, for example, the Lennard-Jones, just write it here again to remind you. I use this epsilon equal 1 and sigma equal 1. Like this. So then you have your minimum. Root of 2 and the position of the minimum at -1. And now what you can do is you do a Taylor expansion. At the position x0, and this can be done for any potential. So you take the potential you have at position x0. I write here LG, but it could be any other potential as well, yeah. Then you have to take the ddx of this potential at position x0 plus, times x minus x0 plus 1/2 d2 dx squared of u, again at this position x equal x0 times x minus x0 squared, plus further terms if you want to explore more of this shape here. But if you stop here, is what we call the harmonic approximation. If I do it for the Lennard-Jones potential, this would be -1. This, for all the potentials, if I take the equilibrium position at this position, this derivative is 0. Here the tangent is horizontal. So that's 0. And we keep only this square term here. Just call it 0 plus 1/2 I did it here for the Lennard-Jones potential. If you do it, you get for the second derivative a strange number. So this d2 is 144 divided by third root of 16. So it's twice square root of 2. But anyhow, I mean, that's not very important. So you get a parabolic restoring energy. Then from this energy you can get the force, restoring force. Which just has a derivative minus this constant term d2 u dx squared times x minus x0. And this means, and I guess you know all harmonic oscillations, this means that the restoring force here is directly proportional to the deviation from equilibrium. This, I guess you all know, leads to harmonic oscillation. So if we write this down, here's the equation of motion. I want to call it, to save some writing, just u double prime times delta x that's the acceleration, or that's the force here, the total term here, and you all know that the solution is given by a sine or a cosine. I think that's more or less high school physics. If we assume here that delta x at time 0 is 0, then we don't have this cosine term. And we can check what this A is. No, sorry, what the omega is. So we take the second derivative. First derivative is A omega cosine omega t. Second derivative is A omega squared sine omega t with a minus sign. Normally it's much easier to do all this with complex functions, exponential ix or so, but in this case I wanted to just show the sine functions, which I don't know how familiar you are with complex e functions. If you put this in here, A omega squared sine omega t is to be minus u double prime A omega sine omega t, and many terms cancel out. Oops, sorry, this omega is not. So the omega square is u double prime over m, or omega the frequency, the angular frequency of the oscillation. I think this, I hope, is familiar to all of you, so that's very simple. But now we make it a bit more complicated. Until here, this would not describe a solid, but just a molecule. Yeah? So you have two atoms bound by such a force, and they start to vibrate. Now, how can we describe a solid? And again, I want to make first a very simple case. And the simplest case is that we consider a linear chain of atoms. And I forgot to mention, but I hope again that this is familiar to you. If you have a spring, this just follows, or ideal spring at least, follows this Hooke's law here, that the displacement is, or the force is proportional to the displacement. Yeah? That's why we call this harmonic forces, and this is typically described by a spring. So we make something like this. We have our atoms here. And they are connected by springs. Now we have to somehow, if we have a finite length of our chain, we have to do something at the ends. And again, we apply periodic boundary conditions. So we close this chain here. No, sorry. I'm even not sure whether this plays a big role. The positions here, x1, x2, and so on, are just multiples the distance here, a. So the positions are just multiples of this lattice constant. And now we can calculate again the force. So we suppose that we displace this atom by a small amount. Oh. I'm not sure why I switched from I to N here. I don't know. In my manuscript, I started with an index I, and then I corrected it to index N, because I was afraid that I confuse it with some other I, but I don't know which. Probably it's the imaginary I. So I switch over to N, and yeah, here it makes more sense, of course, to so the force on atom N, I forgot to define the spring constant here, which would be this curvature, the second derivative of the energy, yeah, but I just call the spring constant K here. So it's this U double prime I introduced here. Yeah. The spring constant, yeah, if we displace this to the right, we stretch the spring on the left and we compress the spring on the right. We assume that only next neighbors feel this displacement. One could do it also for infinite distance, but this just makes it more complicated without giving any more insight. So if we displace here, we stretch this spring by un minus 1 minus, sorry, not u, x. Sorry, no, yeah, u. Equals xn minus, yeah, delta xn or so, yeah. No, un xn 0 minus xn, so this. So these are the equilibrium positions, and this un is just the displacement. Minus I'm even not sure, I don't need this UNs here, because I just consider the differences, so I can stay with the XNs here. So, sorry, I can go back here. Or do I? No, I have to keep it. So this is the left spring here, and now we have the right spring, which is UN plus, no, UN plus 1 minus UN. So this is the force acting on this atom N here. Perhaps I should write it here. K is the second derivative. What we defined before. So if we have the forces, we can write down the equation of motion. Mass times acceleration for this atom N equals this force here. Okay. I have minus K 2 UN here minus and this equation can be solved, similar to what we did before. That's why I have to distinguish the UN, the displacements, and the XN, the positions. So the displacement can be different on every position. Some amplitude times. Now I want to use the complex functions here. I q xn minus omega t. And as I said, we have the positions xn equal n times a and x uppercase in this periodic boundary conditions. We can put this back into the equation of motion. So we, like before, take the first time derivative. Basically, each time derivative gives the factor minus I omega here. And the second another factor minus I omega. This cancels out this minus here, but I have an I squared which is minus 1. So that's the left side of my equation. It's getting a bit narrow here, but I think it works. So if I put this here into this equation, omega alpha exponential I q xn minus omega t times the mass. So perhaps I'll put it in front here. This now equals minus, I think I put it into a new line, otherwise I run out of space, equals minus k 2 un, which is alpha exp I q xn minus omega t minus alpha un plus 1. Still the place is not sufficient. Plus minus alpha exp I q x n minus 1 minus omega t. Now that's done. Okay. And you see that many terms cancel out. So alpha cancels out. Also the exponential I omega t cancels out. So perhaps I just erase it here. So, and the minus sign also. So in the first step, q xn equal K 2 IQ xn minus and now we can use the fact that we have this equal distances, xn is just n times a. And again, you see that we can cancel out many terms, this exponential IQNA. So, I do it as before here. Hope you understand later on what I did here. So, m omega square equals k 2 minus, and here we have exponential, no, I should write it down, exponential IQA minus exponential minus IQA. And do you know what this difference, no, sum of, maybe I should write it this way here, sum of these complex exponentials gives, what it is? Cos two times. And this we can still further modify. This is k, let me see, sine square qa over 2. I should check. 4. So what does it mean? Why did I make this long exercise? What do we get out of it? It gives us a relation between the frequency. What do we have here on the right-hand side? What is this Q? Where did we start? Somewhere here. Here. The Q is a wave vector. It's the inverse of the wavelength, or 2 pi over the wavelength. So this relation between frequency and wavelengths. No, I can put no, it doesn't matter. Looks like this. And that's what we call a dispersion relation. And again, just as a side remark, in quantum mechanics, perhaps you know h bar times the frequency is the energy, and the momentum is h bar times the wave vector. So it also gives a relation between energy and momentum, which I think is not very important for us here, but for many applications, for scattering experiments, for example, it's very important. For example, if you do, for example, neutron scattering, an incoming neutron has an energy given by its velocity, and it also has a momentum, like any particle. And this can excite such lattice vibrations if the momentum more or less fits to the momentum of the lattice vibrations. This way you can measure these dispersion relations in solids. You do neutron scattering, measure the energy and the change in momentum, then you know the energy. If you measure the change in energy of the neutron and the change in energy in momentum of the neutron, then you can get the energy of the phonon which was excited by this neutron. That's the experimental way to determine such dispersion relations. Of Q. Energy of P. I suppose all of you know Bragg's condition for diffraction. This can be also considered as a conservation of momentum, just using these relations here. So, but this is only some extra remark. We can plot this here, or sketch it. Our wave vector and the frequency has a shape like this. I want to have it symmetric. Okay, more or less. And in principle, you could continue it, of course, here. You see there's a maximum frequency. I put a sub d here because this simple one-dimensional chain can be generated, generalized to a three-dimensional crystal. And in three-dimensional crystal, it's also a common model, and there it's called the dBi model. Yeah? And this maximum frequency is a dBi frequency. So it's the maximum frequency you can measure in the crystal, in these lattice vibrations. And this is reached at which q vector. If you look at this equation here, the sine function has its maximum at, what is it, pi over 2. So this is qa over 2 so the corresponding q vector is pi over a. Is it 2 pi over a or pi over a? In my notes I have 2 pi over a, but I think it's pi over a. Did you follow my calculation here? The maximum of the sine is at 90 degrees, yeah, and 90 degrees is pi over 2. That's the way I think. Yeah, so this is pi over 2. So I think my notes are wrong here. So this also means that there's a wavelength, maximum wavelengths, wave vector, shortest wavelengths, which makes sense to describe. Yeah. So the shortest wavelength is the inverse here. Lambda is where is it? Somewhere I have it here. So lambda is 2 pi over q. 2 pi, so it's a lambda min, it's a q max, 2 pi divided by pi over a, so it's, is it 2a or? I thought it would be a over 2, no, I don't know. Anyhow, there's a minimum wavelength. Yeah? Why is it so? And perhaps you heard about the sampling theorem. If you have a signal and you want to somehow record it using digital techniques, you have to sample the signal. How often do you have to sample the signal to get a good representation of your acoustic signal or so? Yeah, I think this factor of 2 is correct. Yeah, so you have to use for the time half of the inverse of the maximum frequency you want to describe. You can do higher sampling. Yeah, you can, if you have periodic signal like this here. So you sample it somewhere here in discrete time steps. Yeah, and it makes no sense to make a finer sampling as this double highest frequency which is contained in the signal. Otherwise, you get some what is called aliasing. Yeah. You can describe the same graph here with this higher frequency, but you get the same points. Yeah? And this is something equivalent to this sampling theorem, what we described here. Okay. I think I will take a bit more time as I expected here for all this. So there's still quite a bit here. Yeah, I think we have to. So the next point which we often need is a density of states. We have our dispersion relation given by this sine function here. Now you might ask, how many of these different possible frequency or vibrations do I have in a certain interval? I marked it. Of course, this is Q here. This is omega. This means we just count the density of the points here. You see here in this part, we have a much higher density of the points. If we make discrete points here, I just invert the axis here for this density. Normally one would put the d of omega as a vertical axis, but I wanted to show it here. So what you do here you have a density which is very high. Here you have a density spacing which is very low. So you expect something like this. And normally, of course, you plot it the other way around. So this is given by two n, and it's a over 2 pi, and it's just 1 over the derivative . That's the slope, yeah, and the slope gives how many points fall into a certain interval. And this is our Q max. One over Q max. And here, if you take the derivative, you get this omega d by a over 2 cosine 1/2 QA. So that's the curve I showed here. And you can simplify this if you express this. I skip these steps. I mean, they are pretty simple. 2n over pi omega d by, if you replace the Q by this maximum frequency, the QA, you find that this is 1 over this curve here. I think I sketched it here on the next slide. Here you see this dispersion relation, bit better sketched here. And here you see the density of states here as a function of the frequency, again inverted. I think on the next slide I have it as we, no. You see that here the density of states that diverges here if you approach this maximum frequency here. Perhaps I should show here an experimental curve or simulated curve here for a real case what these density of states look like. That's this one here. This is this case for tungsten, for which we determined the interatomic potential. This is this solid curve, or this black curve here, is in the harmonic approximation, which I more or less explained here. And here you see the dispersion relation for a real crystal. I think I make it very short how one generalizes it to a three-dimensional system. For a three-dimensional system, you have springs in all directions. You have more possible lattice vibrations, and you have a more complicated crystal structure typically. But the basic approach is very much the same. You have your interatomic potential, you take the second derivative, but not now not only in one direction, but it can be in different directions. You can have coaxial displacements, or you can have shear displacements. So you have different vibration modes. And all this, I'm not sure whether you're familiar with the concept of reciprocal space and all these. This can be represented here in reciprocal space using this so-called Brillouin zone. The Brillouin zone is the counterpart to what I showed here before. That's this point where it ends in this one-dimensional linear chain. It's not a very complicated object. It's just this maximum here. In a three-dimensional object or three-dimensional crystal, you have maximum frequencies or minimum frequencies, maximum wave vectors along different directions with different values. So this is given by this so-called Brillouin zone here. The center, they have all strange letters here. The center of the Brillouin zone is a so-called gamma point, and then along different crystallographic directions you have different letters here. I don't know where they come from. Do you have any idea where this strange notation comes from? So anyhow, and you see that the frequency here for different wave vectors along these different directions, which describes different modes of vibration. So say in the 100 direction, it can vibrate like this. Tungsten has a BCC structure, so it's the same in this direction and this direction. But then there are other directions, like the 111 direction, where typically the crystal is a bit softer, or the 110 direction, and so on. And this is wrapped up here in this type of representation. So here we see from gamma to H, this is along a 100 direction, the vibrations. You see the frequency is a function of wave vector here. Here is along the 11 direction and 110 direction, and so on. So you just put these different directions one besides the other. That's a typical way what people use to visualize these dispersion relations. And I come to this in a moment. No, not in a moment, after lunch. This squares here describe experimentally determined dispersion relation, as I said, via neutron scattering. I think there are also other methods, but that's the standard method. And this is what we obtained, or my student obtained, using these self-made EAM potentials. Here you see two different types of these potentials. You also have different branches. That's another complication. In the BCC lattice, the unit cell, you have two atoms. So you have the vibration of the whole unit cell, and then you can have vibrations of the atoms in the unit cell against each other. These are so-called, one is called acoustic phonons, the other is called optical phonons. Very strange. I mean, tungsten has no special optical properties. This notion comes from the fact that in ionic crystals you can excite these so-called optical phonons, where think of sodium chloride, for example. Sodium chloride has, what is it? It's a FCC lattice for the sodium atoms, and then on the one half, or the body center of this cube, you have the other species. Anyhow, I mean, and if you have such an ionic crystal, they can vibrate against each other. And since these are charged particles, the ions, you can excite such a vibration of the atoms against each other using light. Yeah? That's why they are called optical phonons. They show up in an optical spectrum, while the longitudinal, acoustic phonons cannot be excited by light. Yeah? So that's why we call these vibrations inside the unit cell optical phonons, the other acoustic phonons. And then you have different polarization. That's again a further complication in three-dimensional. You all know that in gases, sound waves are just longitudinal waves. They vibrate like this. In solids, since you have a shear elasticity, you can also have vibrations like this, shear waves. Yeah? So the longitudinal vibrations, they have no polarization. The shear waves, they can vibrate like this or like this. So you have two different polarizations. So you have three modes. That's why you have these three branches here, plus the optical, and that's why you have such a complicated graph. I think sometimes we call this a spaghetti graph. But here on the right-hand side, you see the density of states, and you see certain maxima here. And I think the minima, they can play a particular role. I think next week we will speak about phase transformations. If such a point here goes down to very low frequency, to very low frequencies, that's why I mentioned this transformations into the language of quantum mechanics. Frequency has something to do with energy, or is directly proportional to energy. If the frequency of such an oscillation goes down to zero, means it costs no energy. If something costs no energy, this can happen spontaneously. And this can mean that there's a phase transformation, so that the lattice goes into another structure. We call such zeros here, when this goes close to zero, soft phonons, because they tend to be very soft, they cost very little energy. Yeah, I think I should stop here. Okay, this I think I make after lunch. Yeah, that's again what we discussed yesterday. Okay, so thank you for the moment, and we go on after lunch with the phonons.
We come back at 4 today.
Oh yeah, we have to make a long break now.